Okay, Bismillah ar-Rahman ar-Rahim. We'll continue doing sequences. That was the last one we did. Now we'll go to, actually in this video, we'll talk about these three things, factorial and also monotonic sequences and bounded sequences, and how to check being the sequence converges. If it is bounded and monotonic, then it will converge. Okay, so which is not easy. I mean, not always easy to prove they are monotonic or they are bounded. So we'll deal with some examples. But these are the three main topics in this video. Okay, factorial. What's the meaning by n factorial? N factorial is 1 times 2 times 3 times 4 times n minus 1 times n. This is the meaning of n factorial. Okay. Look, when you wrote it like this, 2n factorial, 2 times n factorial. It's different than 2n factorial. Then the 2n is all factorial. This is n factorial times 2. So it means this is 2, 1 times 2 times 3 until times n. This one is not, is 1 until 2n. 1 times 2 times 3 times n. We are not done. N plus 1 until I reach 2n. So there is a difference. Be careful when you write the factorial. Now, these are the questions in the book. Simplify the ratio of factorials. Okay, let me do this problem just to understand the factorials more. The first one, 17. I have what? N plus 1 factorial over n minus 1 factorial. That will be what? N plus factorial, it means 1 times 2 times 3 until I reach n, until I reach n plus 1. This one is 1. You know what? Let me do this one in a better way. N minus 1 times n plus 1. And I will tell you why. Times 3. This is up to n minus 1 times n minus 1. If you notice, this is similar to this. So these cancelled. What's the remaining? N times n plus 1, which is n squared plus n. So if he asks me, he's not asking this question. He's asking, what is the limit? What is the limit as n goes? I mean, this sequence. If he told me this sequence, an, which is n plus 1 factorial over n minus 1 factorial, converges or diverges. I need to check the limit of an as n goes to infinity. But this one, it is what? N squared plus n, which I know it's infinity. So it will diverge. So sometimes you need to simplify the writing of the sequence to prove it's converge or diverge. Okay. But in this question, just he wants you to rewrite the expression for this, this expression. 3n plus 1 factorial over 3n all factorial. That will be what? 1 plus 2 plus 3 until you reach 3n times 3n plus 1 over 1 times 2 times 3 times 3n. Very clear, this is cancelled with this. I have 3n plus 1, which is easy one. Okay. 19. It will be what? Limit, not limit, what is this? N factorial over n minus 3 factorial. That will be what? Yeah, be careful here. 1 times 2 times 3 times n minus 3, n minus 2, n minus 1, n over 1 times 2 times 3 times n minus 3. This cancelled with this. So what is the answer? N minus 2 n minus 1 times n, or you can simplify it. It's up to, you can do the product to see what will be the answer. 20 for n plus 1 factorial or for n plus 3 factorial. That will be what? 1 plus 2 plus 3 plus 4 times 1 times 2 times 3 times 4n plus 1 4n plus 2 4n plus 3 over the same thing. What is this? Up to 4n plus 1. But here, what this is will be in the denominator. In the denominator, it will be 4n plus 1, 4n plus 2, and 4n plus 3. So my answer, this is cancelled with this. So I have 1 over 4n plus 2, 4n plus 3. That will be my answer. Okay. And as I said, we can now discuss convergence easily. And for example, this one diverge. Yeah, this one diverge. This one also diverge, goes to infinity. This one also diverge. This one no, converges to 0. I have 1 over infinity, which is 0. The limit as it goes to infinity. Now, when the sequence has factorial, either you can simplify it, write it in a way where there is no factorial at all, so you can discuss the convergence. But if the factorial is still there, you cannot use the L'Hopital's rule. You cannot use. Yeah, sometimes you can discuss it. Like sometimes you need to be careful. You cannot use the derivative. You cannot find the derivative for the factorial. So you cannot use L'Hopital's rule. You cannot use all of these things. However, sometimes they're easy. And for example, if you tell me an is 1 over n factorial, for sure the limit is not the same as this one, but I'm talking about limit of an as n goes to infinity will be limit as n goes to infinity of 1 over n factorial, which is n times n plus n minus 1, n minus 2, all of these things, it will be 1 over infinity. So this one for sure goes to infinity as n goes to infinity. So for sure this will be 0, which is different, by the way, than this one. This one I have minus 1 to the power n. Yeah, actually I can do it in an easy way. Yeah, you can do it in 2 ways, because if you remember, we said if I have minus 1 to the power n times an, then I check an, the limit n. If it is 0, then the limit will be 0. If it is not 0 or goes to plus or minus infinity, then the limit does not exist. Okay. So let me do it in 2 ways. I check an, which is 1 over n factorial. What is the limit for n goes to infinity of an? It will be the limit n goes to infinity of 1 over n factorial, which is the limit as n goes to infinity, 1 over 1 times 3. That will be infinity. Infinity. Numbers, who cares? So infinity times the number, it will be infinity. So the answer is 0. So according to this rule, so that means the limit as n goes to infinity of minus 1 to the power n of an, where this goes to 0, is equal to 0. So this sequence, so for sure, the sequence Cn converges to 0. This is one way, which is the easy way. There is another way, which is a little bit complicated. Let me try to explain it. I try to squeeze this sequence between two convergence sequences. Let me see what will happen. If you notice, the second way. I think this is what the book explained. Okay, if you notice, if you put n factorial, it is 1 times 2 times 3 times n. Okay. If you put this sequence, 2 to the power n, it is what? It is 2 times 2 times 2 times 2 n times 2. This one is what? This is times 4. I need up to 4. If you notice n factorial, the first one, n factorial, oops, up to 4. Up to 4, it will be 1 times 2 times 3 times 4. Because why am I choosing 4? Because up to 4, then this will be bigger than this one. At n equal 1, this is 1, 2. So this is bigger. At n equal 2, it will be 2 and 4. So this is still this bigger. At n equal 3, it's 6, and this is 8. So it's still this bigger. At 4, this is what? 24, and this one is 16. So at 4, now we need to consider. So this will be 24 times 5 times 6 times n. Okay, and the second one, 2 to the power n, it will be what? 2 times 2 times 2 times 2, it will be 16 times 2 times 2 times 2. And this is where n is greater than or equal to 4. Okay, why I choose 4? Because I check when this one will be bigger than this one. And after that, after n equal 4, this is bigger than this is bigger than this, and so on, n greater than 2. So that means what? That means n factorial, if you look at it, is greater than or equal to the power n for n greater than or equal to 4. Okay. For n greater than or equal to 4. That means now I can get two things. One, if I find the reciprocal of this, I have 1 over n factorial. Now I'll change the sign. It will be less than or equal 1 over 2 to the power n. This is one thing. Another thing, yeah, which means, or let me, the first one, which means what? Which means also minus 1 to the power n, which will be either negative or positive. If it is negative, for sure it will be less than. For sure, this is less than or equal 1 over 2 to the power n. It's positive, it's still less than or equal, because I have it for the power to be positive, to be even, so that I have a positive value. Now, another thing, I also minus n factorial is less than or equal minus 2 to the power n if I multiply by minus. Okay. Yeah. So that means what? Now, if I find the reciprocal, I have 1, then I have minus 1 over n factorial will be greater than or equal minus 1 over 2 to the power n. In other words, now if I have minus 1 to the power n for 1 over n factorial, that for sure will be greater than 1 over 2 to the power n. Why? Because if this is odd, So I have this relation. If it is even, this will be positive and this is negative. For sure, the positive will be greater than or equal to the negative. So that means what? Yeah, that means I have this is less than or equal to this, greater than or equal to this. Let me write in the second page. So I have minus 1 to the power n, 1 over n factorial. It will be less than or equal 1 over 2 to the power n, and greater than or equal minus 1 over 2 to the power n. Okay. So now I squeeze, this is for n greater than or equal to 4. Actually, I need as n goes to infinity. I'm discussing as n goes to infinity. So for sure, n greater than or equal to 4 is a good one. Okay. So I squeeze this sequence between two sequences. Now I check this sequence, call it Bn, minus 1 over 2 to the power n. What will be the limit as n goes to infinity of Bn? Yeah, it's very clear, it's 0. And Cn, Dn, let me call this Dn. Dn, and this is Bn. Dn is equal 1 over 2 to the power n. What will be the limit as n goes to infinity of Dn? That will be the limit as n goes to infinity, 1 over 2 to the power 2, in which is 0. So for sure, by the squeeze theorem, the limit of minus 1 to the power n as n goes to infinity is equal to 0. So this sequence converges to 0. Okay. Converges to 0. There's a third way to do it. Third way, which is what? Using this theorem. If the limit of the absolute value is equal to 0, then the limit of the original sequence, absolute value of a sequence is equal to 0, then the limit of the original sequence also goes to 0. Now, if we take, they call it what? Cn. The Cn, so it's An is 1 over n factorial. And they know in the 1 over n factorial is less than or equal 1 over 2 to the power n. And also is greater than or equal to 0. Because it's always positive. The n is positive. So that means what? This sequence goes to 0. This sequence goes to 0. So this sequence, by squeeze theorem, goes to 0. So the limit of Cn as n goes to infinity. Yeah, I'm taking the positive, huh? An, which is the limit of absolute value of Cn is equal to 0. That means the limit of Cn goes to 0. So it converges to 0. Okay, Cn, which is the original sequence with the minus 1 to the power n. Okay, so I did this 3 ways. Okay. Another problem, n factorial over n to the power n. When it is we have n factorial, you usually need to be careful. Yeah. What will happen here? Yeah, I need to be careful here. So I have, try to see what's going on with this sequence. I have a1 equal 1. a2, it will be 2 factorial over 2 to the power 2. And that will be 1 times 2 over 2 times 2. a3 will be what? 3 factorial, which is 1 times 2 times 3 over 3 squared, 3 cubed, 3 times 3 times 3. Okay. An, if you continue like that, An, now be careful. It will be n factorial, which is 1 times 2 times 3 times n. Well, let me write it this way. Over n n. Let me write it with times. Yeah. Oops. This one, I can write it 1 over n, 2 over n, 3 over n, until I reach n over n. If you notice, I can do this trick. This is 1. Let me write in a different color. This is 1. This is less than 1. But for sure, 3 is less than n. This is less than 1. So all of this is less than 1. So n is 1 over n times a value less than 1. So this one, all of this is less than 1 over n times 1, which is 1 over n. I hope it's clear. Now multiplying an expression by a value less than 1, sure, it will be less than the same expression times 1. Okay, so that means an is less than 1 over n. Less than or equal, let me see, because if n equal 1, then it will be equal. And for sure, an is greater than 0, because all of these values are positive. All of these values or these values are positive for n greater than or equal to 1. So now I squeeze it between two values or two expressions. And for sure, this goes to 0. And this goes to 0, as in goes to infinity. So that implies the limit of an as n goes to infinity is equal to 0. So the sequence n factorial over n to the power n converges. Yeah, converges to 0. Okay, by the way, this question was in one of the exams, one of the written exams, one of the an old exams, which is the same. No need to do anything here. Okay. Now, these are some common occurring limits. Maybe you can memorize it as formulas, yeah, as examples. And let us see what will happen in these 6 cases, these formulas. First one, what is the limit as n goes to infinity of ln n over n? Okay. How to check? What is my an? It's ln n over n. Where I have f of n is ln n over n. So I have f of x is ln x over x. What is the limit? I'm using the, now I'll use L'Hopital's rule. If I do this, I have what? Infinity over infinity. I have infinity over infinity. So I can use L'Hopital's rule. So I have limit x goes to infinity. 1 over x over 1. And that gives me what? 0. So I have this expression. And I can use this for a problem like this. Ln of n squared over n. This one I can write it as 2 ln n over n. So I have what? I have it similar to this one times 2. So the limit, if I know the formula, the limit as n goes to infinity of ln n squared over n will be 2 times the limit of n goes to infinity ln n over n, and this is 0, so it will be 0. So you can, if you know the formula, you can do it easily. If you don't like to memorize formula, then you need to do it from scratch. Second one, limit as n goes to infinity, nth root of n. This will be what? It will be limit n goes to infinity, n to the power 1 over n. N to the power 1 over n. Okay, I'll do the same thing. What is my an? N to the power 1 over n. what is f of n? It will be an, which is n to the power 1 over n. So my f of x, which is equal to y, it will be x to the power 1 over x. How to do that? To use the limiter's rule, I'll do ln y. That will be 1 over x, ln x. So that implies the limit as x goes to infinity of ln y will be the limit as this goes to infinity of ln x over x, which I just did. And that is 0. That is 0. So that implies the limit of y as it goes to infinity will be e to the power 0, which is 1. So that means the limit as n goes to infinity of the nth root of n is equal to 1. So if I have this problem, the nth root of 3n, this one I can write it as the nth root of 3 with just a value, which is not only a value. This is the nth root of 3 times the nth root of n. So I have what? 3 to the power 1 over n times n to the power 1 over n. So what will be the limit as n goes to infinity of this? 3 to the power 1 over n times n to the power 1 over n. This one, 1 over infinity is 0, 3 to the power 0, which is 1. And this one, from this expression, I know it's what? 1. So the answer is 1. Okay. Now let me do more. This one, limit as n goes to infinity, x to the power 1 over n. What will happen? Yeah, this is an easy one. X is fixed. 3, limit as n goes to infinity, x to the power 1 over n. X is fixed. X is fixed. X just a value. 10, 20, 3, 5, who cares? Huh? Just a value. So this is 1 over, as n goes to infinity, 1 over n goes to 0. So I have x to the power 0, where x is the value. For sure, this goes to 1. So this limit is equal to 1. Where x is positive. Yeah, for sure, x is positive. Yeah, then we have a problem. Okay. Now, I know if I have a problem. Yeah, like for example, this one. -1. No, this is not the second one, I think. Yeah, this one will work with this one. Okay, 4. What is the limit? As n goes to infinity, x to the power n as absolute value of x less than 1. Absolute value of x less than 1. I know that before, huh? What is it for the r? If you remember when we did it for that. Yes. If absolute value of r is less than 1, then the limit of Rn as n goes to infinity is equal to 0. So just you need to remember this. I think it's very clear. Yeah. So this is clear. This one will be equal to 0 if absolute value of R or absolute value of X, that would be equal to 0. The fifth one, yeah, and this one will work. Now my X is equal to -12, where absolute value of X less than 1. So for sure, the limit as n goes to infinity of -12 to the power n, that will be 0. Okay. Fifth one, I have the limit as n goes to infinity, 1 plus x over n all to the power n. I need to find an expression for that. That's an easy one. I let y, yeah. Now we need to be careful about the expressions. Let me change this x to a. Yeah, because I would use x. I use f of x. So we don't want to confuse it with that. It's for fixed x. X is any x. Yeah, but it's a value. Yeah. So I have f of n is an, well, it be n. Okay. So it's not the same as this. A is just a value. So f of x will be 1 plus x over n all to the power n. It will be, no. N is x, huh? A over x all to the power x. And this is y. So it will be ln y. You notice when we have f of x, I change n to x. Huh? A is just a value. Okay. Ln y will be x ln 1 plus a over x. Then I will find the limit as x goes to infinity of the ln y, which is the limit as it goes to infinity of x ln 1 plus a over x. If you use the derivative, if you use this, it will be infinity times 0. This is a over infinity, which is 0, because a is just a fixed value. 1 plus 0, that will be 1. Ln 1 is 0. So you have 0 times infinity. I will use Ripper's rule. Before I do that, I need to make it function over function. So I have this over 1 over x. So now this is what? This is 0 over 0. So I'll use Ripper's rule. Limit goes to infinity of what? I have 1 over 1 plus a over x. Derivative of the argument of ln, which is minus a over x square, over derivative of this, which is minus 1 over x square. So these cancelled. Now as this goes to infinity, this will go to 0. So I have what? 1 over 1 plus 0 times minus a over minus 1. And the answer is 1a. So what will be the limit of y as it goes to infinity? It will be e to the power a, because I have this is ln y. Now I'm doing y. So that means the limit as n goes to infinity of 1 plus a over n to the power n, or let me say x, but that's a value. It will be e to the power x. Yeah, which is this one for any x. Now let me apply it with this one. This one is what? This one is 1 n over n minus 2 over n all to the power n, which is 1 minus 2 over n all to the power n. So the limit as n goes to infinity of n minus 2 over n all to the power n is the same as the limit n goes to infinity 1 minus 2 to the power n over n. So my a is minus 2. Well, my x, it will be, if you look at the formula, 1 plus x over n. So my x is minus 2. So that will be e plus minus 2. Okay. This one, the sixth one, I need to be careful here. Yeah. I need to check the limit as n goes to infinity of what? X to the power n over n factorial. When it is fixed, n is just a value, fixed value. So the trick which I will do, yeah, if you notice, x to the power n over n factorial is what? Is x times x times x n times over 1 times 2 times n. Also, you notice x always should be less than n, because n goes to infinity. For sure, x will be less than n. Okay, so let me rewrite this one, this expression in a different way. I will write it x over 1, x over 2, x over 3, there will come to a time where I have x over x and x over x plus 1, x over x plus 2 times x over n. If that is the case, then you need to be careful. This less than 1, for sure. This will be less than 1. And all of this is less than 1. So this will be less than or equal to x over 1, x over 2, x over 3, until I reach x over x times x over n. Because all of these less than 1. And as n goes to infinity, so this sequence, so I have this sequence, which is always positive, is bounded also, or is less than this. Where you notice this sequence, if I take it, call it Bn, what will be the limit of Bn as n goes to infinity? This is just a number. I don't care what is that number. But this one, a number over infinity, for sure it can be 0. So this will be 0. It will be 0 times a number, it will be 0. So this goes to 0. This goes to 0. So for sure, this one by the squeeze theorem goes to 0. So this sequence, the limit as n goes to infinity of this expression for any x, that will be 0. Yeah. And that is the now, not that will help us. By the way, if x is negative, take the absolute value and do the same thing. So if the absolute value, the limit of the absolute value of an expression goes to 0, then the original goes to 0. So if I have something like this, so my x is 100. So I have x to the power n over n factorial, which is similar to this. So these formulas, if you know them, sometimes they will help. Limit n goes to infinity. X, which is 100 to the power n over n factorial. I don't care what is x. That for sure will be equal to 0. Yeah, I think that's explained the thing somehow. Okay. As I said, the difficulty when you have factorial is you cannot deal with the derivative. Okay. Now let me move to define when they say the sequence is monotonic and the sequence is bounded. What they mean by sequence is monotonic. It means when its terms are non-decreasing, and I have A1 less than A2 less than A3. As I'm going, the sequence increases actually. The value is increasing or they are equal to them. So they say non-decreasing. Or when its terms are non-increasing. So the values are going down or they are equal to the previous one. Okay. So let me do this problem to discuss when these sequences are monotonic or not. Let me go to the first one. A. I know this sequence. This sequence is what? It's if assume I'm starting with an equal one here in all cases. So I have what? I have 2, 4, 2, 4, and so on. 2, 4, 2, 4, 2, 4. So for sure the sequence will not decrease, increase, decrease, increase. Yeah, it's going up, down, up, down. So there is no button when it will go always less than, less than, less than, or greater than, greater than. So this is not monotonic. Not monotonic. Yeah. Go to the second one, which is 2n over 1 plus n. This is the second sequence. Yeah. I have to check, mainly I have to check if it's decreasing or increasing, but also I accept if they are equal. I need to do a trick in this one. Yeah. To check it's decreasing or increasing, I need to check Bn plus 1 and Bn. Either this is always greater than or less than with the equality. So the trick which I will do, I'll write it Bn plus 1. What is Bn plus 1? Means its expression, I'll write it n plus 1 over 1 plus n plus 1. That will be 2n plus 2 over n plus 2. Now we need to compare n plus 1 with Bn. I need to compare Bn plus 1 with Bn. Bn plus 1 with Bn. I don't know. This is greater than or equal. So actually, I will assume something and see I will get it or not. So I have 2n plus 2. I have 2n plus 2 over n plus 2. I know. With 2n over 1 plus n. Let me assume it's less than. See, I'm getting it or not. I know it's greater than, but let me assume it's less than. It will be the same or greater than. What I need, I check this expression. Actually, I try to do it in a way I can go backward to prove it. Then I have what? 2n square. I do this times this, huh? Cross product. I have 2n square plus 2n square plus 2n plus 2n plus 4n. 2n square plus 4n. Okay. Is it? I have 2n square, 2n plus 2n. Well, that will be 4n plus 2. I don't know. Assume less than 2n square plus 2n. So I'm getting what? 2n should be. It will be 2n square plus 4n. Yeah, this is 2 plus n. To n over 1 plus n. No, I want 2. Let me check. This is, sorry. Yeah, this is 2 plus, this is n plus 2, sorry. So this is 4n. Yeah. So I have this cancelled and this cancelled. So I have 2 less than 0, which is wrong. But if I write it greater than, it will be correct. And I tried, I'm making the wrong one because we need to guess, assume positive, negative. So my proof, to prove that Bn plus 1 is greater than Bn will be like this. I start with this one. I know this is correct. So my proof will be like that. Assume 2 is greater than 0. Not assume. This is always correct. I add 2n square. I'm doing this backward now. I add 2n square plus 4n to both sides. Then this is 1 plus n. So I know this is 2n plus 2 times 1 plus n. And this is 2n times n plus 2. Okay. Then I divide Then I divide by n plus 2, and I divide by n plus 1, both sides. So I have 2n plus 2 over n plus 2 greater than 2n over n plus 1. Here I divide by n plus 2 and n plus 1. And this is what? This is bn plus 1. And this, so it's always greater than bn, because 2 always greater than 0. So I'm doing it backward. Yeah. So assume that means bn plus 1 always greater than bn. So it means bn, the sequence bn increasing. Monotonic. Yeah. I think I need more space. This is one way to do it. Another way to prove increasing, decreasing, it will not always. Yeah, you need to try it. What was the sequence? Bn. It was 2n over n over 1 plus n. What I will do, I'll consider the f of n, which is bn. So I will work with this function, f of x, 2x over 1 plus x. I know that if f prime is always positive or non-negative, then it's increasing. If it is negative, then it's decreasing. So this is the way I do it. So I need to check f prime. That will be what? 2, 1 plus x minus 2x over 1 plus x all square. That will be what? 2 plus 2x minus, which is 2x minus 2x gone. So this is always positive. So f is increasing. So this sequence increasing. So this is 2 ways to prove they are increasing. Yeah, the same function. Is it always correct? We can do it this way? No. For example, this case, Cn is very complicated to do it. Yeah. Actually, if you try to find the values, you have at n equal 1, you have 1 over 1. Then you have 4 over 3. Then you have 9 over 7. You have 16 over 15, and so on. If you notice, 1 is less than 4 over 3. But 4 over 3, which you multiply by 7, you have 28, multiply by 3, you have 27. But 4 over 3 will be greater than 9 over 7. So it's not monotonic. Not monotonic. However, be careful. What will happen if from the graph, this is you just notice from the graph. Yes, this one, the difference between this and this, yeah, it's increasing here, then it's decreasing. But after that, it will decrease all the way. But it is, yeah, this is, I don't think, easy to prove. But I think decrease as n greater than or equal to 3. From here, all the way, it will decrease. Okay, which is not easy to get unless you have the graph of the sequence. Okay, let me go to another example. Proof decreasing, increasing. Yeah, this sequence, and he says it's decreasing. Yeah, let me check. I need to check bn plus 1. Well, we'll call it an. My an is 3 over n plus 5. Yeah. So what will be an plus 1? Sometimes it's easy to finalize. That will be n plus 1 plus 5, which is 3 over n plus 6, which is for sure. Now I have 3. if I had to compare this with this, I have 3, I have n plus 5, n plus 6. Always n plus 6 will be greater than n plus 5. Since it's in the denominator, that means it's less than 3 over n plus 5, which is an. So I'm getting what? An plus 1 less than an. So the sequence decreasing. Okay. So the sequence decreasing. This one, how to prove it? There are 2 ways. The first way, using the same trick we did before, this trick, I will do an plus 1, which is n plus 1 over n plus 1 square plus 1. And that will be what? And that will be, yeah, be careful, n plus 1 over n square plus 2n plus 1 plus 1 plus 2. I need to do this, an plus 1 and an, less than or greater than. I know. So let me do these things. Actually, I'll prove it's what? It's decreasing, so it will be less than. I'm sure it will be less than. Yeah, you can do it either way, but until you get the answer, then you can do it backwards. So I have what? N plus 1 over n squared plus 2n plus 2. I assume it's less than this. I do cross product. Be careful now. N cubed plus n squared plus n plus 1. Since the values are positive, I have n greater than 0, 1, and so on. Huh? So it will make it easier. I need to show this is always less than. This is I have n cubed plus 2n squared plus 2n. Yeah. I'm not sure and I did not do any mistake. No, let me do the calculation, see what will happen. I'm sure I did it correct. N squared plus 2n plus 1 plus 2. Okay. This is n cubed plus 2n squared. This is 2n squared, sorry. Plus 2n. Wait a minute. Yeah. I have this times this. I have n cubed plus n squared. I have n plus 1. This is n over n squared plus 1. Okay. Plus n squared plus n plus 1. Less than. I want to prove this is less than n cubed plus 2n squared plus 2n. Take it to the other side or take it to this side. So I need what? This is cancelled. I take everything to the other side. So I have n squared plus n plus 1 to be positive. Yeah. Okay. Will that help? Yeah, and this is always positive. Why? Because if you add, I took this to the other side, n squared plus n plus 1. If you add 1 over 4, which is half the coefficient of the middle term, and I subtract 1 minus 1 over 4. So this will be n plus half square plus 3 over 4, which is always positive. So this is correct. So it's decreasing, or you can do it the other way, which is, I think, easier. If you do it this way, so you have what is f prime. It will be x squared plus 1 minus 2x times x over x squared plus 1 all square. Am I right? Yeah, derivative of 1 x is 1 times x squared plus 1 minus 2x times x. So you have what? So you have 1 minus x squared over x squared plus 1 all square. And this is actually proof is going to prove it's decreasing, huh? So this one is less than or equal 0 when I have 1 minus x squared less than or equal to 0. Yeah, if you do it, this is minus 1 and this is 1. Actually, need only the positive side since n is positive, but let me do it for all. I have, yeah, take a negative value. That will be negative. That will be positive. That will be negative. So for x greater than or equal to 1, this sequence or this function will be decreasing. And this is what I'm concerned about because the sequence is defined for n greater than or equal to 1. So that means for n greater than or equal to 1, this sequence decreasing. And this function is, and do it this way or that way. Okay. Let me define the bounded, and then I will try to do some examples about it. And in another, just yeah. Let me explain the quick ones, and then I will do some difficult one. Then I will do some exercises from the book about these bounded and monotonic. Sequence is bounded above when there's a real number m, so that the sequence cannot exceed that number. And we call m the upper bound. We say bounded below when the sequence always greater than or equal that number. A sequence is bounded when it is bounded above and bounded below. Okay. If we took the sequence n is bounded below but not bounded above. Why? Because I know n is always greater than or equal to 1. I'm starting with 1. Yeah, I'm thinking in the sequence, the starting point, 0, 1, who cares? N is always greater than or equal to 1. So it's bounded below. So there is n always greater than or equal the value, which is n. So it's bounded below. So it's bounded below. However, the limit as n goes to infinity of n is equal to infinity. So I cannot bound n from the other side. So it's not bounded above. There is no value. I can say n is less than or equal that value. I cannot say less than or equal something. This I cannot do because the limit goes to infinity. Okay. The sequence n over n squared plus 1. This sequence n over n squared plus 1. How to show it's bounded above or bounded below? N over n squared plus 1. Yeah, if you notice, yeah, I can bound this. It's bounded. Why? Think about it. I know n always less than or equal the square plus 1 for n equal 1 and so on, for sure. This is, I think, easy to prove. So now this sequence, so that means n over n squared plus 1 less than or equal to 1. So this sequence n over n squared plus 1 always positive less than or equal to 0. Yeah, if it's starting with 1, yeah, but I can write, yeah, no need for the equality, but it's bounded below by 0 and always less than or equal to 1. So it's bounded below by 0 and above by 1. Cannot exceed 1 and it's always greater than 0. Okay. Let me now try to do the sequences which we did here. Where is it? Example 9. The sequences we started with when we talk about increasing, decreasing. Yeah, these three ones. Okay. The first one, which was, forget what was it, is 3 plus minus 1 and 1. It's 3 an. Let me write it here. 3 plus minus 1 to the power n. Which is, I know it is, if n equal 1, it will be 2, 4, 2, 4. So for sure, an, I can write is between, cannot exceed 2, cannot be less than 2, and it cannot be more than 4. So it's bounded. So we say an bounded. An bounded. Now we'll come to the second one. What was the second one? To n over 1 plus n. Yeah, bn to n over 1 plus n. Can I bound this? To n over n plus 1. Yeah, let me check it here. Let me do it here. By the way, not always you can do. Let me check the values. See, I'm going easily. I can prove it or not. Yeah, sometimes you need to do it by something called mathematical induction, which I will explain later. This will be at n equal 1, it will be 2 over 2. At n equal 2, it will be 4 over 3. At n equal 3, it will be 6 over 4, which is 3 over 2. Yeah. Can I check in 2n? Can I say, yeah, let me do it this way. Now for n greater than or equal to 1, 2n will be n plus n. And I know n is greater than or equal to 1, so this is greater than or equal 1 plus n. So 2n over 1 plus n, 2n over 1 plus n will be greater than or equal to 1. This is one way. Okay. Table of this side. For the sequence always greater than or equal to 1. Now to prove the other side, I know that I want to prove this is less than or equal to n. I know n, take n over 1 plus n. Or let me say, yeah, this is, yeah, to prove that means bn greater than or equal to 1. Now, also check this. You need now to play with these things. Huh? So I have 1 plus n always greater than or equal to n. So it means n over 1 plus n, it will be less than or equal to 1. Now multiply by 2. So I have 2n over 1 plus n less than 2. So that means this sequence is less than or equal to 2. So it's bounded between 1 and 2. Yeah, so it means Bn is bounded between 1 and 2. Sequence n we did, n over n plus 1. Actually, I can make it between 0. We did it here. This is less than or equal to 1 and less than 0. And greater than 0 and less than 1, yeah. Is it always you can't do it this way? No, sometimes it's too difficult to do. Like in this sequence, n squared over 2 to the power n minus. I don't think you can do it easily. By the way, yeah, this will be the maximum, which is 4 over 3. But I know it's for sure it's greater than or equal to 0. But how to get this number, it's not an easy task. Yeah, let me stop here because what we will do later, why we are talking about bounded and monotonic, because you have this theorem, and this is what I will do in the next video. If I have bounded, if a sequence is bounded and monotonic, This is enough for us to say it's convergence, and I will explain it in the next video. I don't like to have long videos. Then I will do examples from the book. I'll stop the recording. Thank you.